setting up the live stream. All right. So that is all set. We are live streaming now. So let's get started. Hello, good morning. Hope you guys are having a nice day. So today we are continuing on in our chapter 3, and I wanted to sort of remind you about this weird split that we have. So we're going to start what's called the chain rule today. We are not going to finish the entire chain rule section. It's pretty long and pretty detailed. So we'll do about half of it today, and then we'll cover the second half when we get back from spring break. So you don't have a quiz on the chain rule until after spring break. The only thing that's still due before spring break is the 3.2 homework. And I also want to mention the 3.5 homework. So some of you have emailed and said, what's this 3.5 homework? If you click on it, you'll see it's just sine and cosine, which we covered in 3.1. There's 5 problems on it. It's pretty fast. So that is meant to be there. So today we'll cover the first half of the chain rule. And then, like I said, after spring break, we will cover the second half. So I'm going to go ahead and switch over to the dot cam. Okay. All right. So one of the most complicated things about the chain rule is trying to understand what the chain rule is doing. Like, what is it? Why are we using it? The computation piece, once you get the hang of it, is not so bad, but we want to make sure conceptually that we understand what the chain rule is and why we're using it. So we're going to spend a few minutes here at the beginning really sort of focusing in on that particular question so that we have a good foundation of understanding why we're using this rule and where it comes from. So the first piece of information we need, okay, is that when we were back in, I think, let's see, 1.8, we talked about something called composite functions. And composite functions are when you plug one function into another function, okay? So we have composite functions. The chain rule is used to take the derivative of a composite function, okay? So if we have a composite function and we want to take the derivative of that function, that's when we have the chain rule. And the reason I'm going to sort of be specific about this is because after we do the chain rule, we're going to use the rules that we would use for if two things are multiplied together or if two things are divided. And so those are sort of the 3 big categories of more advanced functions that we're going to learn how to find the derivative of. So this is the first one. And again, we're dealing with composite functions. So one function plugged into another one, okay? And so the sort of map of what we're going to be doing with these composite functions really comes from thinking about composite functions and limits and derivatives. So I want you to think about a composite function where the g of x, or the inside function, that we call that z, okay? Which means we can write the outside function as y equals f of z. Now, why would we write z instead of g of x? Well, that will become more apparent as we think about the process. So we are assuming for all these situations that the functions we are working with are continuous and differentiable, that there's not anything weird happening with these functions. So if we were to make a small change in x, okay, so z equals g of x. If we changed x by a little bit, that means z would change by a little bit. And if z changes by a little bit, that means y will change by a little bit, right? So a small change in x also results in a small change in y because of the nature of composite functions. So if we think about these small changes, right, in ratios, that is what we were doing when we were looking at things like secant lines, okay? And when we let these small changes go to 0, that's when we got derivatives. And so this doesn't look like how we got derivatives because this is how Leibniz did it. And we did our work mostly Newtonian. But hopefully, when you look at the sort of this next step, you recognize these Leibniz derivative notation. And so what we're trying to get to here is that if you want to take the derivative of y with respect to x, of some complicated composite function, then we can take the derivative of y with respect to z, where we're doing this z substitution, times the derivative of z with respect to x. So think about what you know about fractions, right? These dz's will cancel, and you'll be left with dy dx. Now, that may sound complicated. You may think, why would we do that? And the idea is that this, the thing we want, is complicated, right? So it's up here, a composite function that we don't know how to deal with. But these two derivatives are basic derivatives. And again, basic is not easy. It means they go back to that chart. So if we can consider these basic derivatives, we can then get the derivative of the more complicated one, okay? So this is sort of our map of what we're going to be doing a lot of the time. However, there is an alternative way to think about the chain rule using Newtonian notation. And that says if you take the derivative with respect to x of f of g of x, so some composite function, it's going to equal the derivative of the outside function, derivative of f, with g of x the same inside, times the derivative of the inside function, so of g of x. So these are the two general formulas for the chain rule, okay? And it's a really good idea to have these general formulas pulled out and written somewhere, you know, on a note card or at the front of your notebook, so that you can always keep in mind what the general formulas are. Because what you're going to find is that we're going to apply them in specific circumstances in specific ways. Sometimes we have to revert back to the general form. So these, again, are the same thing. This is the Leibniz notation. This is the Newtonian notation. And we'll sort of see that we're going to rely more heavily on the Leibniz notation, but every once in a while this sneaks in. So before we get to it, like the big examples that we're going to start working through, I want to give you a scenario of why we would want to think about things this way and what kind of information we can get. Okay. So suppose that the amount of gas that a vehicle uses, G, in gallons, depends on the distance traveled S in miles, right? So that makes total sense. The amount of gas you use depends on how far you've gone, okay? The distance traveled S, so how far you've gone, depends on time T in hours that the vehicle is moving, okay? So how far you go depends on how long you drive, okay? So far, so good. If 0.05 gallons of gas is used for each mile traveled, okay? So now we're talking about the relationship between gallons and miles, and the vehicle is traveling 50 miles per hour, right? That's the speed it's going. Then we can use these two rates to calculate how fast the gas is being consumed, okay? So gallons of gas over time. So here in this scenario, the information we have is 0.05 gallons of gas is used for each mile traveled, right? So here we're talking about gallons and distance. So that's dg ds. That's the rate at which this is changing, the gallons per mile, right? And we know that that is 0.05, and we'll put the units underneath. Right? You'll often hear people talk about gas in terms of, you know, gallons per mile when they talk about how much it costs. We also know that when we take whatever this journey is, that we're traveling 50 miles an hour. Okay, so that's a distance over a time. So 50 miles per hour. And if we were to multiply these together, what we would get is dg dt. So think about what these derivatives look like and what the resulting one is. And so when we multiply these two numbers together, we get 2.5. And then what about the units? So the miles units are going to cancel, and we get gallons per hour. So we are able to determine the amount of gas we're using per hour by knowing these other two rates. right? So this is sort of a composite function in the wild where we have some information, we're thinking about how to apply it, but this is meant to highlight that if you want this particular rate and you know these other rates, right, this ds will cancel, which is the miles part once we have our units, and give us the rate that we want. So we need to think about how to put all of these ideas together. And it's not super straightforward when we start it. It's a little clunky. So if you're feeling like, what are we even doing here? Trust the process. It does get easier the more of these we do. But we're going to start with some really sort of general examples of the chain rule that show up in different types of ways. So we're going to start with a table. Okay. And so this is sort of the general application of the chain rule, and then we'll get into more specific applications after we do some general applications. So when we have a table, I want to talk about how we get the values of these tables. So what this is saying is that f of x is this column. So if you want to know f of 2, you would go to f and you would go to 2, and that would give you a value of 3. So f of 2 would equal 3. These are the derivative values. So f prime of 2 would equal -1. G prime of 2 would equal -3. That's sort of how you read that table, is that you go to the function you're interested in, and then the x value that you want, and then the middle value is the dependent value you're looking for. So what types of things might we ask having to do with a chain rule? So having a table like this where you have a function and derivative values often indicates that you're going to be doing a chain rule or one of the later rules that we're using. So what we need to do is we need to look at the function as it's given in the problem. So part A says determine if y equals f of g of x is increasing or decreasing at x equals 3. So the thing that we notice first, the important piece of this, is how the function is defined. So for both A and B, we see a composite function. So f of g of x, g of f of x. Seeing that the function is defined this way leads us to think chain rule. That's the first step. Now we also know for both of these that we're interested in what's happening at 3. So we need to think about how we can apply the chain rule to evaluate this at 3. And so I'm going to write it up here since we just started doing this. I'm going to write the notation for the chain rule. And I'm going to write this in Newtonian notation. And the reason I'm opting to do it this way is because what I'm given in the table are functions, f, g, f prime, g prime. So that means I want to be able to write the rule with its functions. So I have f prime of g of x times g prime of x. So that's the rule when you have f of g of x. So if I'm interested in if the function is increasing or decreasing at 3, what I'm interested in is whether the derivative is positive or negative at 3. Because remember, the derivative will tell us if the function is increasing or decreasing based on the sign. So for part A, I need to plug in a 3 wherever I see an x, and then I need to find these values on the table to put them together. So that's what you're going to be trying to do. See if we can get some practice on this. For part B, you need to think about how we need to adapt the formula when we have g of f of x instead. So notice the composition is slightly different. So we have to adapt this formula. And then for part C, find the equation of the tangent line. So this is sort of a stretch. I want you to think about what we need to find the equation of a tangent line, right, from the processes we've talked about before. We need a point and we need a slope. So the question is, can we get the point? Can we get the slope? So I'm going to have you try that and see if we can sort of put that all together. So I'm going to give you about 3 minutes to try these out. Feel free to try them out in any order, and then we'll go through them together. And so again, this is sort of brand new, and I'm asking you to just try something. So even if you have no idea what to do, just try something, right? Because that helps you sort of eliminate things that may not work. But we will go through it pretty thoroughly in about 3 minutes. So try it out. Okay, take about 30 more seconds. All right, so let's go through this and let's start with part A. So here again, we have the composite function f of g of x, and we're interested in what's happening at x equals 3. Since we're asking the question if the function is increasing or decreasing at 3, we need to look at whether the derivative is positive or negative. If it's positive, then our function's increasing. If it's negative, then our function's decreasing. So to get the derivative of f of g of x, we're going to do f prime of g of 3, because we're evaluating it at 3, so we're going to plug in a 3 wherever we see an x, times g prime of 3. Okay, so now we have to figure out how do we get these values and what do they mean. So there's sort of two pieces to this. We have this part of the function times this part of the function. So let's start with the first part. We have f prime of g of 3. So first we want to start by finding g of 3. So we're going to go to our g function. We're going to go down to 3, and we get a value of 2. So that's going to get substituted in for g of 3. So now we have f prime of 2 times g prime of 3. So what I did is I substituted in the g of 3 value. So now I need to find f prime of 2 times g prime of 3. F prime of 2 means we go to the derivative function, we go down to 2, and we get a value of -1 times g prime of 3. So g prime of 3, we go to the g prime function, right? We go down to 3, and that's going to give us a value of 1. So we have -1 times 1, which is going to give us -1. And so the actual number itself is not as important as the sign, because we're really interested in whether the derivative is positive or negative. So here we see that the derivative is negative. And if the first derivative of a function is negative, that tells us that the original function is decreasing at that point. Okay, so we're using some of the information we had from previous sections about the relationship of the sign of the derivative and whether the original function is increasing and decreasing. But now we're bringing in these chain rule problems to start thinking about these values. Okay, so let's look at part B. So for part B, there's sort of two things we need to do. We need to figure out what does our derivative look like if we change this to g of f of x, and then we need to do the same process of evaluating what's happening at 3. So let's start with just thinking about the derivative. If we have g of f of x instead of f of g of x, that's going to change our derivative to be g prime of f of x times f prime of x, right? So those are going to switch because we switched the order, okay? So now, when we think about evaluating this at 3, we have g prime of f of 3 times f prime of 3, right? So again, we need to figure out how to get these values. So we're going to start by finding f of 3. So we're going to go to the f function. We're going to go down to 3, and that's going to give us a value of 2. So now we have g prime of 2 times f prime of 3. Okay. So when we do g prime of 2, we're going to go to the derivative g. We're going to go down to 2, and we get a -3. And then f prime of 3, we're going to go to f prime we go down to 3, we get a value of positive 5. And then again, we're going to multiply those together. Negative 3 times 5 gives us negative 15. And then we have to take that value and use it in our context. So again, we're taking our final value and saying, hey, is it positive or negative? Because that tells me something about the original function. So since this is negative, that tells me that the original function is decreasing at 3. So both f of g of x and g of f of x will be decreasing at x equals 3. So even though we don't know what the function is, we do know some of the behavior because of this analysis that we're doing. And again, this is very new. So, if you didn't figure that out, that's totally normal. That's why we're doing it together. So now let's move on to part C. Find the equation of the tangent line at x equals 1. So again, in order to get the equation of a tangent line, we need a point and we need a slope. Doesn't matter which one we find first. So let's talk about the point. So we know to get the point, we need to plug the value into the function we are evaluating. So if we were to plug in x equals 1, we have f of g of 1. So to get the y value, we have to work from the inside out. So we did this a little bit in 1.8. So g of 1 means we're going to go to the g function. We go down to 1 and we get a value of 3. So now we have f of 3. So f of 3, we're going to go to f. We're going to go down to 3 and we get a value of 2, which means that our point is 1, 2. Right? We found that y value. So now we have our point. To get our slope, this is where we're going to bring in our chain rule formula. So notice that the order here is f of g of x. So we're up at the top, f of g of x. So to get our slope, we're going to do f prime of g of, now here we're interested in what's happening at 1, times g prime of 1. And so now we're going to work through these values like we did before. So g of 1, we're going to go to g, we go down to 1, we get a value of 3. So we have f prime of 3 times g prime of 1. Okay. So f prime of 3, so we go to f prime, we go down to 3. That's going to give us 5 times g prime of 1. So we go to g prime, we go to 1. And that gives me negative 4. So 5 times negative 4, which tells me that the slope of my line is going to be negative 20, right? So 5 times negative 4 is negative 20. So now I have a slope and I have a point. So I need to put those together with y equals mx plus b. So we have y equals negative 20x plus b. We plug in our point, 1, 2. So when x is 1, y is 2. Okay, so we're going to add 20 over to the other side. And we get b equals 22. So then our final equation here, let's see, where can we write this? So they'll have enough space. We'll write it right up here, is y equals negative 20x, so that's our slope, plus 22, which is our b. Okay, so again, we need to find a point, we need to find a slope. That's the same whenever we're finding the equation of a tangent line. What's different here is the function that we're working with. Okay, so those are some of the ways that we can apply the chain rule in sort of a more general way when we have a table. Okay, the next example we're going to consider is how we might think about the chain rule when we have a graph. Okay, so we're going to look at a picture, and on this picture, there's going to be a graph of f of x and of g of x, and then we're going to use that to try to think about some chain rule derivatives here. So f of x is a linear function with a downward slope. G of x is a linear function with an upward slope. So we're told here that h of x is f of g of x, and that k of x is g of f of x. So these are the two ways we can compose these two functions. And we want to use these graphs to find h prime of 1 and k prime of 2. And so as just a reminder, I'm going to put the formulas down here that we talked about. So if we have f of g of x, the derivative is f prime of g of x times g prime of x. And if we have the alternate composition, g of f of x, we get g prime of f of x times f prime of x. Okay, so these are the two formulas that we've talked about. And so if we're looking for h prime of 1, h was the f of g of x, so we're looking to evaluate this at 1. So f prime of g of 1 times g prime of 1. So what we need to do is think about how we could use this graph to find these particular values. Okay, so I'm going to give you 2 to 3 minutes. I want you to try to think about this. If nothing else, see if you can just set up the formula we're looking for and find the values you feel comfortable with, right? So just remember that if you're looking for g of 1, you're looking for a functional value, whereas g prime of 1, you're looking for the slope of the tangent line. Since the functions are linear, the slope of the tangent line is the same as the slope of the line. Okay, so take 2 minutes, see if you can figure one of these out or both of these out if you have time, and then we'll go through the process together. Okay, take about 30 more seconds. All right, well, let's start with h prime of 1. So we need to go back and remember which way the function was composed for h, and h was f of g of x, which means that when we're thinking about the derivative, we are thinking about this particular form of the chain rule. So we have to plug in a 1 wherever we see an x. So we start by just writing that out. So we have f of g of 1 times g prime of 1. So these are the values that we have to try to figure out to see if we can determine this value here. So I'm going to start with g of 1 because it's on the inside. You could start with g prime of 1. Those are separate things. That's just a matter of preference. So for g of 1, what I'm going to be doing is I'm going to be going to the g function, which is the red one. I'm going to go to 1, and I'm going to see what the y value is, right? So I'm looking for the functional value here. So g of 1, to me, looks like it's going to be at the value of 4, right? So the y value is going to be 4. So I'm going to substitute that in, and now I have f prime of 4 times g prime of 1. And so when I think about what these are the slopes of the tangent lines at 4 for f and at 1 for g. But these functions are linear, which means they have the same slope everywhere. So I'm going to find the slope in general for these two lines, and that will tell me the slope for f and the slope for g. So let's start with the slope for f. Okay, so to get the slope of the f function, I need to pick 2 points on the function. And so here I see the point 8, 0 and the point 0, 8. Those seem the most convenient to me. You can pick any 2 points on the line, and that's totally fine. So to find the slope, I'm going to do the change in y over the change in x. So the change in y is 8 minus 0 divided by 0 minus 8. So we end up with 8 over negative 8. So the slope of my line is negative 1, which means that the derivative at any point is going to be negative 1 because my function is linear. So that means that f prime of 4 is going to be negative 1. I'm going to do something similar to my g function. I want to get the slope of the line. So let's see. I'm going to use this point here. So I have the point 0, 2. And then I also already have the point 1, 4. So I'm just going to go ahead and use that since I already found it. Okay. And again, you can pick any 2 points on this line. You should get the same slope. So again, we're going to do change in y over change in x. So the change in y, we have 4 minus 2, which is 2, divided by 1 minus 0. 1 minus 0 is 1. 2 divided by 1 is going to give me a slope of 2, which means the derivative at any point is going to be 2 because all those tangent lines will lie on the line. So here I can go ahead and I can fill in that slope of 2. So now I can multiply these two values together, and I get h prime of 1 equals negative 2. Okay, so that's all the background work happening here. And there's a lot, right? There's a lot of background things happening. We have to remember how to find equations and slopes of lines. We need to remember the chain rule. We need to remember composite functions. We need to remember how derivatives relate to linear functions. So there's a lot going on here, okay? Now let's go ahead and think about our other question. We're looking for k prime of 2. Okay, so again, I want to reference what my k function is. And here it's g of f of x, which means that I'm using this version of the chain rule where these have been switched. So that means I'm doing g prime of f of 2 times f prime of 2. Okay, so again, I'm going to start with my functional value, f of 2, to see if I can determine what that is going to be. So for f of 2, I'm going to go over to 2. I'm going to go up until I hit the f function, which is the green one. And then I'm going to come over and see what the y value is. To me, that looks like a 6, right? So I'm going to go ahead and call that 6. So g prime of 6 times f prime of 2. And again, these are linear functions. So g prime of 6 is going to be the slope of the g function at any point, right? And so here again, that's going to be 2. And then f prime of 2, again, is going to be the slope of the f function. And that's going to be negative 1. Excuse me. So 2 times negative 1 gives me negative 2. So k prime of 2 is going to give me -2. So we're using the graph to help us fill in these values in the formula. And so we're pairing what we know about graphs and derivatives into the rules for the chain rule. So this is sort of the general way that we would use the chain rule for tables and graphs. And so this is sort of, I would say 15% of the time, this is how we're using the chain rule in sort of a more general way, okay? 85% of the time, however, we're going to be doing this more algebraically. So we're going to be doing this on particular functions, right? We're going to be using the formula with actual functions that we're working with. And so because we're working with something complicated and trying to break it down into easier pieces, it turns out that we actually have sort of 4 different maps to do this depending on the type of chain rule. So we're going to go through 2 of those today, I believe, and then, we'll do the other ones later. But what I want to say about this before we do the algebraic ones is that the process is going to be the same for all of the types, but the first step of doing any of the algebraic chain rules is recognizing the type. Okay, so that's something that we want to practice. We want to think about what the function looks like so we can determine which process we're using. Okay, so we're going to walk through an example very, very carefully, very detailed, talk about all the pieces and how to do it. But before we do that, I just want to highlight, like I was saying, the type. And so the type that we're going to start with is what is known as the power rule type. So remember when we started talking about derivatives, we had things like x to the 10th, x to the 20th, x to the 40th, right? X to the -12. Something similar here. When you have something raised to a power, that is the first type. So these are chain rule functions that are raised to a power. So that means you have some base raised to some number, and that number can be a whole number, it could be a fraction, but it has that similar structure to the power rule. So that's the first type. So the one we're going to start with is 3x plus 4 to the 10th. And so what we do when we think about starting the chain rule is we need to break this up into 2 basic functions, right? And the way we do this is through a substitution. So the way the substitution works is that whatever is in the base that's being raised to the power, we're going to call that z. Okay, so here z equals 3x plus 4. And after we've said what is in the base, we're going to rewrite our y as z to the 10th. So we take that base and we change it to z. And the reason we want to do this again is if you now look at these 2 functions individually, right, these follow our basic rules for derivatives, and we'll talk about how in a minute, whereas this one, we don't really have a rule yet. Okay, so what we're going to be doing is we're going to be relying on the Leibniz version of the chain rule formula for these types, for the algebraic types. And so what this says is we want dy dx, right? We want the derivative of y with respect to x. The way we're going to get there is by finding the derivative of y with respect to z times the derivative of z with respect to x. So what does that mean and what does that look like? So again, we start by making our base equal to z. So I'm going to write this again, just a little bit bigger. Z equals 3x plus 4. And so one of the things we need is dz dx, which is the derivative of z with respect to x. I want you to notice that z is our dependent variable, x is our independent variable. So if we were to take the derivative of this function, it would be dz dx, derivative of z with respect to x. So when we take the derivative, we go term by term. So 3x, the derivative of 3x is 3. That's a linear term. The derivative of 4 is 0 because it's a constant by itself. Now, the second function we have is our new y function, right? Which is y equals z to the 10th, right? Because after we called our base z, we wrote y as z to the 10th. So now we can use this to get this derivative, dy dz, the derivative of y with respect to z. So dy dz means that we can use our basic rule and treat z as our variable, which means here the 10 is going to come down and we're going to subtract 1 from the power. So we get 10z to the 9th. So now we have dz dx, dy dz. And what this says is if we multiply these two things together, we're going to get dy dx, which is the derivative that we want. Okay, so we're going to start by literally setting this up exactly as the formula states. So dy dx equals, now dy dz is 10z to the 9th times dz dx. dz dx is 3. Okay, now when we write it just like this, there's one little problem. We were looking for the derivative of y with respect to x, and our answer has a z in it. Okay, so we found the derivative, but it's not quite done because we have one more step of simplification. And when we do this step, we need to plug back in what z represented. So our final answer is in terms of x. So we can multiply the 3 and the 10. That's going to give me 30. Now my z is raised to the 9th power. So I'm going to use parentheses. So my z is 3x plus 4 to the 9th power. So that means my final derivative is 30 times 3x plus 4 to the 9th power. Okay, so again, what is the process here? We're going to do a substitution. Z is the base that is raised to the power. Then we rewrite it with y as z raised to that power. We write these down. We find each of their derivatives. We multiply their derivatives together. Then once we've multiplied them, we substitute back in for what z represented. Okay, so that's like our process that we're going to be using here. So I'm going to have you try another one here. And this one is 3 minus x cubed to the 7th. I kind of wrote over it, so I'm going to write it over here. So y equals 3 minus x cubed to the 7th. Okay, so I want you to start by writing out what is z, what is the base here. Once we have z, how do we rewrite y with a z in it? Then you're going to find each of their respective derivatives and multiply them together. Okay, so try it out. I'm going to give you 2 minutes, see how far you can get, and then we'll go through it together. Okay, take about 30 more seconds. All right. So again, we want to define z as our base. So here that is 3 minus x cubed. Excuse me, I'm very sneezy today. And then we need to rewrite our function with the z in it. So now we're going to put the z and substitute that into the base. So our y becomes z to the 7th. Once we have those, we want to find each of their respective derivatives. So the derivative of z with respect to x, the derivative of 3 will be 0 because that's a constant that's by itself. And then the minus x cubed, the derivative will be minus 3x squared. So the power comes down and we subtract 1 from the power. For z to the 7th, dy dz, the 7 is going to come down. And then we're going to subtract 1 from the power. So 7z to the 6th. So now we need to multiply these two things together to get the derivative we want, which is dy dx. So dy dx is going to equal negative 3x squared times 7z to the 6th. We know that we do have to substitute back in, and we do want to simplify our constants. So how do we do that here? So the negative 3 and the 7 can be combined to give us negative 21. The x squared doesn't combine with anything. There's no other x squared terms. So we have x squared. And now we have z to the 6th. Well, we don't want the z there anymore. So we go back to what z represents in terms of x. And we get 3 minus x cubed all to the 6th power. Okay, so again, we multiply our two derivatives, but then we have to substitute back in for z, and we have to simplify up our constants. Okay, so this is the general map of how we approach these types of problems with something raised to a power. And this particular approach is based on how Leibniz developed the chain rule. If we think about it in terms of how Newton did this, we can also think about this in terms of our f prime of g of x times g prime of x. And this is sort of a hybrid of Newton and Leibniz together, but this is sort of a shortcut. So this is like, how do I want to say this? This is one way you can think about it as long as you keep in mind what's happening in the background. So if you want to take the derivative of something raised to a power, okay, so we have z raised to the n, where z is some function of x. We can use the power rule, where the power comes down, the base stays the same, we subtract 1 from the power. That's just the general power rule we had before. But then we have to multiply that by the derivative of the inside. Okay, so what does that mean? So we're thinking about this in a new way. And so let's go back to the last problem we were just looking at and think about how we would reason through this, just thinking about this idea of the outside function and the inside function. And so what we would do here is we'd say, okay, 3 minus x cubed to the 7th. The first thing we can do is deal with the power. The power comes down and we subtract 1 from the power. So if we were to do that, we would get 7 times 3 minus x cubed to the 6th. That's just dealing with this power of 7. That's what this piece says. But then we have to remember to multiply that by the derivative of the inside. So that's when we go to this part, just the base, and we say, well, okay, we have to multiply by the derivative of that. So the derivative of this piece is 0 minus 3x squared. Okay, so again, this says take the derivative of the outside, which talks about the power. Everything inside stays the same. times the derivative of the inside. And then when you simplify that, right, you would multiply the -3 times the 7, and you get the same thing that we get by doing a z substitution. So some people like to think about it like this. I call this the outside-inside rule. You may have heard that if you've taken calculus before. And so what that does is the outside part of the derivative, which is the power, gets dealt with in the first step, times the inside derivative. So the outside-inside rule. So if your brain sort of processes that and that makes sense, you can certainly use this outside-inside rule to do this a little more quickly and more efficiently. And the reason why that might be helpful is because as things start to get more complicated, which they won't until next class, sometimes doing the chain rule is the first step in a many-step process. So if you can do the derivative faster, then that just helps you save a little bit of time, right? But it's a matter of preference here. So let's keep practicing this. I'm actually going to give you both of them to try. So the first one is sine x plus 2 to the 5th. I'm just going to write this a little bit bigger because this seems small to me. So we have sine x plus 2 to the 5th. Think about trying to use this sort of idea of the outside-inside rule. See if that feels okay. And then the second one, we have e to the x plus x squared minus 1 to the -3. Okay, so again, we have some base raised to a power. So try those out. I'll give you 2 to 3 minutes. Try it with the shortcut. If you really don't like the shortcut, you can definitely do it with the substitution. And then we will go through these together. But these will be good practice in setting these up and both seeing more forms that are of this power rule form where we have a base raised to a power. So try that out. And then in a few minutes, we'll go through it together. Okay, take about 30 more seconds. All right. So for the first one here, my base is sine x plus 2, and my power is 5. So if I want to try to use my shortcut here, what I'm going to do is I'm going to deal with the power first. That's the outside part. So when I deal with the power, the 5 comes down. Everything inside stays the same. And I subtract 1 from the power. So 5 times sine x plus 2 to the 4th. That's the outside part, okay? But then I have to remember to multiply this by the derivative of the inside. And so when we say the inside, we mean the derivative of the base. So we look at the sine x plus 2, and we say, what's the derivative of that? The derivative of sine is cosine, and the derivative of 2 is 0 because it's a constant. So my final derivative is 5 times sine x plus 2 to the 4th plus cosine x. So you would get the same thing if you did a z substitution as if you thought about it as outside inside. I also want you to note that there's 3 factors here. Okay, there's a little bit of an algebra note here. So these 3 factors, you can exchange their positions. So you can write this as 5 times cosine x times sine x plus 2 to the 4th, or you could write sine x plus 2 to the 4th times 5 times cosine x. So if you've done out a z substitution and you have these 3 factors and they're just in a different order, then that is the same thing. Okay, so whenever you do out a chain rule and you're looking at a multiple choice answer, you want to look at the answer and make sure the factors that are in the answer are the same as the factors in your answer. They may not be in the same order, but as long as the factors are all there, it's an equivalent statement. Okay, so now let's look at y equals e to the x plus x squared minus 1 to the negative 3. So again, my base is everything down here in parentheses, and my power is negative 3. When I take the derivative, if I use the outside inside rule, I deal with the power first. So the negative 3 comes down. Everything inside stays the same. And I subtract 1 from the power. So negative 3 minus 1 is negative 4. So we still have to be careful with that even in the chain rule. But then I have to multiply that by the derivative of the inside, which is the derivative of the base. So I go term by term. The derivative of e to the x is e to the x. The derivative of x squared is 2x. That's the power rule. And then the derivative of 1 is 0 because that's a constant. So my final derivative looks like this. Okay. So again, if you like thinking about it as the outside inside rule, you will get the same answer as if you prefer the z substitution. Okay, either one is fine. It's really a matter of preference. I will say that the outside inside rule is a little bit faster, but it will get you the same answer. Okay, so now that we have a good sense of how to do the chain rule on a power function type, let's go ahead and do our common example here. I want you to find the equation of the tangent line to the function square root of 3x plus 10 at x equals 2. And the one sort of reminder I will give you is that the square root is the same thing as the 1/2 power. So once you write it as a 1/2 power, we have it in the form of one of our power functions. So hopefully you're getting used to the process of finding the equation of the tangent line. The derivative is obviously what is different here from other examples. So I want you to try it out. I'm going to give you 2 minutes, see what you can figure out, and then we will go through it together. Okay, take about 30 more seconds. Okay, so when we find the equation of a tangent line, we need a point and we need a slope, right? So it doesn't matter which one we do first, but I'm going to go ahead and find our point here. So we're interested in what's happening at x equals 2. So if we plug a 2 into our function, we get the shared point. So we have 3 times 2 plus 10. 3 times 2 is 6. 6 plus 10 is 16. The square root of 16 is 4. Okay, so that means our shared point is 2, 4. So now we have our point. Now we also need the slope. So in order to do the slope, we're going to have to find the derivative of this function. And so what I'm going to do is I'm just going to rewrite my function right up here with the 1/2 power so we can sort of see the map of where this derivative is coming from. So we have 3x plus 10 to the 1/2 power. We got to turn it into the 1/2 power because otherwise the symbol will sort of trip us up. We can't do anything with the symbol. We got to have a numerical power. So when I go ahead and do the derivative, I'm going to do it in general first. So here the 1/2 comes down. Everything inside stays the same. And I subtract 1 from the power. But then I have to remember to multiply this by the derivative of the base. So the derivative of 3x is 3, and the derivative of 10 is 0. So my derivative looks like this. And on the surface, we are just doing the process that we did before. However, in order to find the slope in the next step, we do have to do a bit of algebra to think about what this function looks like and what it's going to mean when we plug in the 2. And so I prefer to simplify before I plug in. Some people like to plug in and then simplify. It doesn't matter which order you do it, but we do need to do a little bit of algebra to simplify this in order to then be able to plug in our slope. So when I simplify, I'm going to bring the 3 to the front, and I have 3 over 2. And now this has a negative power. And so I'm going to deal with that by putting it back down in the denominator to make that power positive. And then once it's positive, I'm going to turn it back into a square root. So I get 3 over 2 times the square root of 3x plus 10. Hopefully you sort of remember that from algebra and those steps make sense. But again, I brought the 3 to the front to multiply the half. That's these two constants here. I brought this whole term down to the denominator, which makes this positive. And if you have something to the positive 1/2, that's the same thing as the square root. So now I'm going to plug in my x value. So I have 3 over 2 times the square root of 3 times 2 plus 10. So what do I get here? So I have a 3 on the top. Now on the bottom, I end up with the square root of 16 times 2. So that's 4 times 2, which is 8. So I get 3/8. 3/8 can't be simplified. So my slope here is going to be 3/8. And my point is 2, 4. So I need to put those together. So y equals 3/8 x plus b. Now I'm going to plug in my point. So when x is 2, y is 4. Okay, so I have 6/8 over here. So I have to do 4 minus 6/8. So since I'm going to be subtracting eighths over here, I'm going to turn my 4 into eighths. So I have 32/8, which is the 4, minus 6/8, which is this, to get my B. Okay, so 32/8 minus 6/8 is going to give me 26/8. And we can either leave everything in eighths to be consistent, or you could simplify this to 13/4. Okay, that's going to be the same thing, but we still need to put it all together into y equals mx plus b. So let's see, let's come up here to the space. So we have y equals 3/8 x plus b. I'm going to leave my b in eighths so that everything is in eighths. So plus 26/8. Now, I will tell you that when we do these types of problems, in my experience in the past, students had no trouble, eventually finding the derivative once they've practiced that process a bunch. Where things get more complicated is in the algebra and simplifying. This is where students tend to make more mistakes. So again, if it's been a while since you've done algebra, you definitely want to be extra careful with these and make sure you're sort of reviewing them with someone in Drop and Help or something like that, just to make sure the algebra isn't sort of getting in the way of your understanding of calculus. Okay, so that's the equation of the tangent line. I'm gonna stop here just because I think it makes sense, but just so you know, when we get back from the break, we're gonna start with exponential type chain rule. So this was the power rule chain rule. And I strongly recommend that you go to the homework before you leave for spring break. So tomorrow, tonight, and just click through and try one or two of the ones with a power function structure. You're looking for ones that have a base raised to a power, or some that are like the general table or graph types, and try one or two homework problems before you leave so that you can really solidify how this works in your mind before we get back. Okay, so have a great spring break, and I will see you all when we return.